No, that doesn't want to show. Uh, let me quickly. I'm sorry. Um,
Everything okay, Han? Can we help?
yeah. I should share my screen again. Sorry for this. So hopefully this will work. Yes. Can you see the movie now? So on the left are some of the first images that the DKIST has been able to observe of the solar surface. On the right are the same images but degraded to the level of resolution that our current high resolution telescope, the Dunn Solar Telescope in Sunspot, New Mexico, was able to achieve. And you can see that there is really a very clear
Han,
improvement in the resolution of these
the,
images.
the movie is not actually playing. Would you like me to share it so people can see what you're doing?
It's not playing?
No. If you stop sharing, I can open the movie
Okay.
and share it for you.
Okay. That's going to be...
Can you all see this?
Yeah. So as you can see, there is a clear, very clear improvement in resolution and a very clear hope that we will do a lot of discovery science with this unprecedented resolution that the DKIST now enables. So thanks, Claire. Let me share it again. So what is the motivation of these workshops that we are organizing? Of course, we cannot directly measure physical quantities like magnetic field strength, temperature, line of sight, velocity on the solar surface. Instead, we have to infer those quantities from the intensity and its polarization state. And radiative transfer tells us how these physical quantities modify the absorption and emission coefficients and are mapped into the polarization spectrum. And therefore, we can use spectral inversions that use this knowledge to uncover the reverse of this mapping in a mathematically rigorous way, where we can infer the physical properties from the spectrum. An application of such inversions on level 1 data is what we call level 2 data production. Now, the NSF very kindly provided us with additional funding to set up a program that is now that allowed us to create the NSO Community Science Program as a division within the NSO. And the funding for this will be used for two main tasks, namely seeding level 2 expertise at US universities and develop new methods and produce standard products of level 2 data and make those available to the community. So the way we do this seeding of level 2 expertise is we organize workshops like these. We run the DKIST Ambassador Program, which is a program in which we offer shared funding for a number of PhD and graduate students and postdocs at different US institutions so that they can spend their time in writing proposals, doing DKIST observations, and doing level 2 production of data. And hopefully some of their results and methods will be made available to the wider community. We are developing at the NSO new inversion methods to measure chromospheric magnetic fields with non-LTE inversions, to measure coronal magnetic fields. And we are planning on making some of these products standard. If you do observations with a certain fixed setup, we will make those observations available and invert the level 1 to level 2 products. As you all see, this workshop is really meant to be interactive. Let your voice be heard, learn by doing the exercises. I think this is really important. So I wish you welcome again to this workshop, and hopefully in the coming years you'll have the opportunity to explore very new DKIST science, very new solar science with the DKIST. Thank you.
Thank you, Han. I think that now I wanted to give you all a sense of the program and how that will develop, and then after me, Claire will say a few words also on this, using breakout rooms, using the Slack channels, and this. Although we have already done some of it. So let me see if I can share my screen.
Gianna, give me 1 second to finish taking the
Oh, yes.
picture.
Please,
if you
tell
have
me.
turned off your camera, please turn it back on, because everybody has gotten sort of moved around a little bit. So please turn your camera on and look at the camera, and we'll take a quick picture, and then we can move on.
I'll just wait for you to say.
Okay. Yeah, sorry. It'll take about 1 minute.
Yep. I will admit people in the meantime.
I've turned off the waiting room.
Oh, okay. So they just come in then.
Yeah.
So how come the number doesn't change?
Okay. Last one. Okay. Thank you, everybody.
Thank you. So I wanted to show you the program preview. I think this is the one that I want to share. I hope it's the right one. Can you see? Yes. Can you see the program?
Yes, we can.
Yes. Okay. Thank you very much. So as Han mentioned, this is completely new to all of us. Please be patient. We'll learn as we go. I had nightmares about it last night. So it's just like, hopefully. And if there is something that you think could be done better, please just tell us and comment and so on. So the plan, you've seen it several times already. The blue things are the actual lecture where you are all welcome to come and listen to in real time, and also ask questions in real time as we go. Or for some people that might be in not very favorable time zones, they can opt to watch the lectures later on the YouTube channel. Of course, the YouTube channel will have the speaker, the answers to questions, and so on. You will not have any chance of reading the questions in real time or asking questions yourself. The lectures have been planned so that every 15 minutes or so, the speaker will stop to give everybody a chance to ask, clarifications or questions that you need to do at that point. Let's see. Then there is the exercises are all in orange, and this is where we will split into groups. And actually, we will be asking the second group, and you know who you are, to log off, and we will just continue with the first group. Within the exercises themselves, there is some times, some short periods where people will have more like a school, like another small lecture in them. And this will not be recorded, but will be repeated in the second week when we will have the second group doing the exercises. Then finally, the whites are some sort of general discussions. And so, for example, for the second group, tomorrow and Wednesday, they could just log in a little later if they want, because this discussion will mostly be about the exercises that were done the day before. Please note there has been a slight change that I will be sending around later today. So we switched the Friday, the late Thursday afternoon and early Friday morning, so that we have the general discussion about the exercises on Thursday at the end of the day. And then instead, early on Friday, we have all the discussion. We can all have the discussion of the research paper. And again, I will be sending this later on. And then finally, on Friday, we have a day which is not fully, but in big part dedicated to DKIST. So there will be introduction to DKIST and an update on the status of the telescope and the instruments, an update on the first call for proposals, and something more detailed about the level 2 project that Han just mentioned. And then in the afternoon, there will be examples and exercises together about running one of the instrument performance calculator for the VISP, which is an instrument that is being offered in the first call for proposal. And we did this on purpose to put everything at the end of the week, because during the week, hopefully you will get a sense of what kind of data you might need to do the science that you want to do. And so at that point, you will be able to use the instrument performance calculator in a more meaningful sense, because you know what kind, for example, of noise you need to have to be able to invert your data and things like this. And so that's about it. And now I give it to Claire to give a few practical issues about the breakouts and so on. Thanks.
Thanks, Janet. I'm going to stop sharing.
Yes, let's see, how do I do this? Stop share, there.
For those of you who don't know me, my name is Claire. I'm the head of education and outreach for NSO, and I'm going to be helping with a lot of the background stuff this week. So if you have questions or technical difficulties or anything like that, don't hesitate to get in touch. The easiest way is on our Slack channel, which I'll show you in just a few minutes. While we are going through the workshop, and this is true for the whole week, so please don't hesitate to ask questions in the chat window during presentations. You can drop your questions in at any time, and then at appropriate times, I will interrupt the speaker with the questions, and that will just help to keep things a little bit more streamlined. As Jenna said, we'll have breaks for questions at regular intervals, so you can also unmute and ask your question verbally, but if you'd like to get it recorded before it leaves your head, you can put it in the chat window. You're also welcome to ask questions on the YouTube link that we'll share. So every time we start a new section, I will start a new YouTube stream and put the link to that in the Slack channel, and it will also go on the web page. And so if you get kicked off of Zoom and can't join here, you can watch on our YouTube stream, and there's a live comment section there that you can also ask questions if you can't get back onto Zoom for some reason. And then finally, I want to show you the Slack channel for anybody who may not be familiar with Slack. I encourage you to use this as an excuse to try it out. We will be using this quite extensively this week, and hopefully afterwards, after this workshop is over. So there are multiple channels that might be of use to you. We have one here for the software installation. We have a general channel where we'll post the YouTube links and so on. So this was the YouTube link for this session right here. We will have during the exercises, so during the discussion, the breakout sessions and so on, any specifics can go in the exercises chat. So it's a pretty standard Slack channel, but it's also gives you the opportunity to communicate with people directly. We will have a number of breakout sessions throughout the week at different times. So when that happens, you will be asked to go into a breakout room with between 1 and 4 or 5 other people, depending on the exercise that we're doing at the time. So during those breakouts, please participate, turn on your microphone, your camera. This is an opportunity for you to, really compound the learning that you're getting during the lecture part of the sessions this week. And during some of the breakouts, we will be making little broadcasts. So they appear at the top of your screen in a little green box, usually about breaks and finishing up time. So I'll give you like a 5-minute warning. During some of our breakouts, they'll run into the break. So I'll let you know when the official break starts, but we will leave the breakout rooms open so you can continue to work if you want to, but you don't have to. So if you want to take your break and walk away, that's entirely okay. And we encourage that. But if you're super enthusiastic and really don't want to step away just yet, then it means that you can keep working in your breakouts, and then we'll pull you all back automatically. So
one extra comment, Claire. In the breakout room is like a normal Zoom room, so you can share your screen with your cohort in that particular room.
But in the breakout rooms, you can't communicate with everybody. So if you need to post a question to somebody, you can either ask for help. There's a little button that says ask for help, and then we will find you one of the experts who knows how to answer your question, or you can put your question directly into the Slack channel and somebody will join your room and help you out with it that way. So just know that if you're in a breakout room in Zoom, you can't communicate across other breakout rooms. So that's one of the limiting features, and why we want to encourage you to use the Slack channel concurrently with Zoom. So if you have questions or technical issues or anything like that, you can send me a private message on here and I'll do my best to help you, or you can get me on Slack and again, I'll do my best to help you, and we will we'll try and get you as sorted as we possibly can.
Okay, I think that was what we had to say. Are there any questions? You can use now you can even speak up if you wish, right? So, or do it in the chat. So before we start with the actual lectures. Everybody seems fine. We give it another couple of minutes. It's not even 11 yet, so we were faster. Oh, I have actually a question that might be of interest for everybody. Where are all the channels of the Slack thing? Because you showed one that I don't have.
Yeah, so you can explore which channels we have. If you click on the plus sign beside channels and go to browse channels, know that this channel, this Slack channel was started for the spectral polarimetry school that we ran 2 years ago. So there are archive channels, don't worry about those. I'll post in the general channel all of the ones that will be relevant for the workshop today.
Good, thank you.
Does anybody have questions or concerns or things that they are particularly interested in hearing about today?
Questions or exercises? Okay. Very good.
So I just had a question to say that somebody is not sure about which group that they're in yet. I'm assuming you mean breakout group. We haven't assigned the breakout groups yet, so don't worry about that just yet. That will happen automatically when it's time to send you to your breakout rooms. You will just be sent to the room without much issue.
You don't have any recourse. You'll be just
you have no choice in the matter.
You have no choice. So we'll be, I think at the beginning we'll do some random, so because it's, I don't know, it's a lot of work to try to decide who goes with whom and so on. But we'll see how that goes. Okay. Do you think anybody will join in the next 3 minutes, or we can just go with the lecture and use these extra 3 minutes?
Started.
Yeah, we can get started. So our first speaker is Han Uitenbroek, that will be given a lecture about radiative transfer, the formation of spectral lines, something which is the basic of the things that we'll be doing this week. And so as mentioned before, there will be several pauses throughout the lecture. And then at the end of the lecture, there will be our first break. It will be about noon time here in Boulder. And then we'll have our first break of half an hour. Okay, Han, I think you can start.
Mm-hmm. Let me see. Can you hear me?
Yes, we can.
And can you see the screen now?
We can.
Okay. See if it works. So I will talk a little bit about a very elemental theory of line formation, with the idea that you hopefully will understand why we see spectral lines and how we can use them. So let me first, is this playing now, the movie? No? Can you see it playing now?
Yes, now it's playing.
Okay, then I'll do it this way. So what you see is a movie made from images taken with the INODE satellite, so above the Earth atmosphere. And in this movie, you see the image change from blue to orange. And while it does this, it changes from a wavelength that mostly sees the atmosphere lower down, and to a wavelength that sees the higher layers that are really dominated by the magnetic field. You see this very streaky nature of the atmosphere that is really an indication that the magnetic field dominates the motions and the structure of the atmosphere there. Well, here in the blue, you can see that most of the atmosphere, let me stop it, go back a little bit. You see the granulation, you see waves like waves in water. These are the 5-minute acoustic oscillations. But you see that the atmosphere here is mostly dominated by hydrodynamic forces. What I want you to take away from this is that the solar atmosphere is highly structured, is very dynamic on time scales ranging from a few seconds to the 11-year cycle. And also that when we look at the sun at different wavelengths, we can see different things. We see different aspects of the atmosphere. And we will exploit this feature where a different wavelength shows different layers of the atmosphere to retrieve information from the atmosphere using spectral lines. I'll let it run for one more time. And you see when you switch over to orange, which is a light that comes in the calcium line, one of the calcium lines in the near ultraviolet, you see the magnetic field takes over the higher layers of the atmosphere. Ideally, we would be able to measure, we would like to be able to measure all the properties of every pixel in this atmosphere, measure the magnetic field, and this is what we try to do with spectral inversions. You've all seen this movie, probably, of the first DKIST images. These were not done with spectral polarimetry yet, but we should be able, once all the instruments will be online, to take images like this and take spectra of each pixel in the atmosphere, meaning that in principle, we should be able to determine the physical properties of each of these locations in this image at this kind of resolution and time resolution. So what do I want you to take away from this talk? One thing is that opacity varies with wavelength. Different wavelengths, therefore, probe different layers. When the opacity at a certain wavelength is higher, we probe higher layers of the atmosphere. When the opacity is lower at a certain wavelength, we look deeper into the atmosphere. Opacities vary strongly across a spectral line, and I'll show you how and why. But this is one of the main points that I would like you to take away. The core of the line, where the opacity is high, forms higher in the atmosphere than the wings and the continuum around the line, which form deeper in the atmosphere, which provide us information by photons that escape from those layers about those deeper layers. An absorption line occurs when the intensity in the core originates from a cooler layer than from which the continuum originates. This seemingly very simple statement is not so easy to understand once you start looking at the line formation theory. But in the end, it is this simple fact that the core of the line has a lower intensity because it comes from a layer that is cooler than the continuum. When we do measurements, it requires a physical model. In this workshop, we will be talking about the approximation of the Milne-Eddington approach. This is a very, how to say, limited, somewhat limited, but very useful physical model. But it means that the uncertainties that you have in your measurement, even if you fit the line profile perfectly with your method, are tied to the model that you use. And the model is not perfect. It makes some approximations, it makes some assumptions. To give you an example of how we use model, this is the spectrum at this center of the sun. Now, I want to measure the temperature of this. And I can say, well, let's assume that the solar radiation that comes from the surface is a black body. And I now try to fit black body curves of different temperatures to see which one matches best. And I see that none of them really matches very well. This tells me two things. At different wavelengths, I probably look at different layers of the atmosphere. So I cannot represent the spectrum of the sun with one black body spectrum, because it really is a combination of black body spectra at different wavelengths. And this tells me that I can make an approximate measurement. Looks like somewhere between 6,000 and 6,300 Kelvin is a reasonable guess. But my model is not perfect. It has problems. One of the things that you can see is that at the near infrared, between 1500 and 2000 nanometers, I have a much higher temperature. And the reason for this is that the continuum opacity varies strongly with wavelength. This is a plot of the H- opacity at different wavelengths. H-, the hydrogen atom actually is capable of capturing another electron, forming the H- ion, and it has two different transitions. It has a bound-free transition, where the additional electron is ionized, is decoupled from the atom, and it has a free opacity, which is strongly wavelength dependent, as shown here with the blue curve. This free opacity is a free electron zooming by a hydrogen atom and exchanging energy. As you can see, is that exactly where I had this excess temperature in my intensity curve, the H- opacity is a minimum. So there I look to the deepest layers that I can see in the visible and near infrared, actually at all wavelengths. So again, this is just a simple example to show you that the results that we derive are very tightly coupled to the model that we use to measure those values that we try to observe. One warning, when I say that a certain wavelength comes from a certain height in the atmosphere, this is an approximate statement. This is now an image of the solar granulation. You see the granules, you see the bright grains here that are associated with stronger magnetic field concentrations. And this now is a vertical cross-section through, at this position, through the atmosphere in this image. And you can see that the temperature in the granules and the intergranular lanes at a given geometric height is very different. Also the opacity, which comes from the H minus mostly in the continuum, has very different opacity here and here. So at a given wavelength, the intensity will come from higher layers in the granules and lower layers in the intergranular lanes. So keep this in mind. This variation may be several hundred kilometers in the photosphere. So when I talk about the formation height, this is kind of an average over the surface, not a specific height in the atmosphere. So what am I going to talk about? I will introduce the concepts of intensity, absorption, emission, the transfer equation, and the source function. I will show you how the Eddington-Barbier relation is very useful in this case. I show you how we can explain limb darkening with an atmosphere that has lower temperature the further we go out. And I'll show you how the same effect causes spectral lines. You've all seen images like this. This is actually not an observed spectrum, but this is a theoretically calculated spectrum where the colors have been added artificially. But it shows the tens of thousands, hundreds of thousands of lines in the visible, many more in the blue than in the red. It shows some very broad lines, H alpha, the sodium D lines, the magnesium B lines, calcium H and K, somewhere hidden in the blue here. And all of these, of course, we know are due to different elements, to electronic transitions between different electronic states in the different ions and atoms of different elements. Each of those have different properties. So each of those, some of them form at deeper layers, some of them form at higher layers, some of them are sensitive to temperature more than others. Some of them have more magnetic sensitivity. All of these properties of these spectral lines can be used to measure properties of the solar atmosphere once we understand the theory of this. Here's a different representation of the spectrum in terms of a line plot. These are the calcium H and K, the broadest spectral lines in the visible part of the spectrum. And here are the sodium D lines. You see they are much narrower. You see again that there are many more spectral lines in the blue. This is just a fluke, if you will, of atomic physics, that there are many more electronic transitions at energy differences between different atomic levels associated with these wavelengths than in the red part of the spectrum. But all of these lines can be used to measure properties in the solar atmosphere. One example, for instance, is if we take the spectra at this slit position, if you will, artificially, this column of spectral points in the image, we plot the spectrum. We plot the circular polarizations, for instance. You see that the spectral line shape varies very much with location. You see line shifts where the granules are shifted towards the blue because this is upflowing material. You see the line shifting to the reds in the intergranular lanes because these are downflowing regions. And you see that where there are bright points, there is significant circular polarization, an indication of the presence of magnetic field. We come to all of this later, but just to show you that when we have spectrally resolved polarimetry at high spatial resolution, we can measure all these quantities in the solar atmosphere, as long as we apply the theory of our understanding of spectral line formation.
Can I pause you for 1 second?
Yes.
We have a question, I think, on the previous slide.
Yes.
What are the units of the x-axis in the right images?
In the right images, this is polarization percentage, so 1% in polarization, in the circular polarization. This is relative intensity, where the continuum is close to 1, and the line core, the darkest area, is close to 0.2. So this is intensity as a function of wavelength divided by the intensity in the continuum.
Okay, so wavelength is on the x-axis.
Wavelength is on the x-axis,
Okay.
yes.
Thank
And
you.
on the y-axis, it is position along the slit.
Great.
So to go into the theory of radiative transfer and how spectral lines form, we need to just define a couple of quantities. The radiation field, the specific intensity, I, is the radiative energy that flows at the location R per second per wavelength interval per solid angle in the direction L through a surface area dA perpendicular to the line, to the ray, the direction in which I flows. Intensity is a conserved with distance. Intensity coming from the sun does not change between the solar atmosphere and the Earth atmosphere. Of course, in the Earth atmosphere, there's absorption and emission, and the intensity changes. But in the absence of any of these processes like emission, absorption, and scattering process, intensity is a conserved quantity. It does change when there's absorption. And when there's absorption in a little element that is crossed by the ray, the intensity is decreased by an amount alpha, the absorption coefficient, times I times the path length across this element. So this basically defines the absorption coefficient. Note that the absorption, the attenuation by absorption in this element is proportional to the intensity. Then there's emission. In the same way, we have defining the emission coefficients, which add energy or intensity to a ray over an element ds with the emission coefficient J. Now, if we add both absorption and emission processes across such an element, we see that the change in intensity is what is added by emission in this little slab minus what is absorbed in this little slab. And we can write the equation of radiative transfer in this way, where the IDS is the emission minus the absorption. And we can then define the quantity S, which is now the source function, which is a very important term. And it looks like a bit of a random definition, but you see that it makes very much sense in terms of rewriting the transfer equation. And we have an additional quantity, which is optical path length, the absorption coefficient times ds. So this is a very simple but deceptively so simple equation, in that a lot of the difficulties in this equation are hidden in the microphysics, namely the absorption and the emission processes that make up the emission and absorption coefficients. And the fact that in general, the source function is actually a function of I. So in general, this is not a closed equation. So the source function, by this rewriting of the equation, is determined as the emission divided by the absorption processes or coefficients. Now, when you have several processes at one wavelength, you cannot just add up the source function. You have to add up the emission coefficients and the absorption coefficients before you take this ratio. So you can rewrite then the source function in this simple case. And typically there will be not only one line, there may be many lines, there may be different absorption coefficients. So this is a much larger sum than just the sum of two processes. But this shows you as a simple example how you can rewrite the sum of a source function or the total source function as the weighted sum of two contributions, namely the contribution of the continuum and the contribution of the line. Now, when we write the source function in this way, we can, with a simple transformation, rewrite this differential equation as an integral equation. You just apply integrating coefficients e to the minus tau. You probably have all learned how to do this. You should try it yourself if you don't know and look it up. But we can transform this differential equation in a very simple way into an integral equation. And this integral equation is called the formal solution. Again, it is not a closed equation in this case, because in general, this source function will also or can depend on the intensity itself. In our case, we will, in these lectures this week, we will make the simplifying assumption that the source function is actually the Planck function, that we are working under LTE conditions, and that the source function is only a function of wavelength and of temperature, and nothing else in the atmosphere. So in the simple case now that we have a source function that is constant with height and a opacity that is constant with height, you can actually solve this equation. It is a closed equation under those conditions. And the solution, the exact solution, is then that the intensity coming from a slab of thickness d is the intensity that impinges on this slab, I0, plus the source function times e to the minus e minus tau, the optical path length, the total optical path length through this slab. Now you can see if this optical path length is large, this term, the intensity falling onto the slab, is actually completely attenuated. This term goes to zero, this term goes to zero. So the emergent intensity from this slab, if it's very optically thick, is equal to the source function. If tau of d is much less than 1, this term here becomes 1 minus tau, the same here. And so the intensity at the surface of the slab becomes I0 plus the attenuated S minus I with tau. Okay. Are there any questions so far? No? Okay. Now assume
Well,
that
is that your pause for questions, or do you have the break?
Well, I mean, I thought we have two breaks, so this would be a reasonable time to have a break.
Okay. So let's pause for a second and just see if there are any questions that people haven't asked yet. This is a good time to unmute yourself and ask an oral question if you want to, or you can post a question into the chat. Just give people a second to type their questions if they have any. Okay, you might be good then. If you have questions, feel free to drop them in and I'll interrupt Han with them.
Okay, shall I continue?
Yes, please.
Okay, so now let's assume we have what is called a semi-infinite plane parallel atmosphere. Semi-infinite because the atmosphere goes to infinity the deeper we go. Basically, you assume, and we know, that the optical depth goes to infinity because the atmosphere is so thick, the sun is so large when you go deeper. And plane parallel means that the atmosphere does not vary in property in the horizontal direction. So we just have a semi-infinite atmosphere that is constant at equal height in all directions. Then let us define optical depth. Optical depth now goes down. So hence we get this minus sign, that d tau is minus the absorption coefficient times dz, which goes down, which goes up, dz goes up, but the optical depth goes down, over mu. And you can see that mu, the cosine of theta, comes from the perspective at which you look, the angle at which you look into the atmosphere. So with this, we can rewrite the transfer equation as function of optical depth. Now, not optical path length along a ray. There are two things that you should note. There's a factor mu that comes from this, and there's a change in sign. We have now I minus S. This sometimes is very confusing, and it confuses even the best of us when we write a program, because we have to think hard in which direction we follow the path. But as a function of optical depth, the equation of radiative transfer is I minus S. So now we can write the formal solution of the emergent intensity at optical depth 0 at an angle mu. And the formal solution you can follow from the previous slides. You can rewrite it like this. Now, let's assume that the source function can be written as a power series in optical depth. And using this mathematical quantity, where the integral of 0 to infinity of e to the minus tau, tau to the power n dt is normal n. We can find the solution, insert this source function into this integral, and find the exact solution. And we see that we get that the emergent intensity is a power series now in mu. If we cut off this power series and assume that the source function is linear in optical depth, we see that the emergent intensity at the surface of a semi-infinite plane parallel atmosphere is equal approximately to the source function at tau equal mu. This is now shown in a graph here. This is now an atmosphere. You can take the color, for instance, as the variation of temperature, and with that through the Planck function as the variation of the source function, where the temperature is higher when it's deep and lower when you're at higher layers. And you can see that when I take this Eddington-Barguet solution and I calculate the intensity for a vertical ray, I get that the intensity is equal to the source function, where tau is equal 1. Now, when I look at an angle in this into this atmosphere, I sample the atmosphere just because of the projection of this at this angle of the path through the atmosphere. I see that I measure the intensity here is equal to the source function at tau equal mu, where mu is less than 1. And so I see that the intensity for ray B should be smaller than that of ray A. So now we are in a position to understand limb darkening. This is an image of the sun in a continuum wavelength, and you see that even though there is small scale variation, there is a global pattern that shows that the intensity at this center is larger than the intensity towards the limb. And we can understand this the following way. When we look at this center, we look perpendicular to the surface. And so therefore we see deeper layers than when we look at an angle into the atmosphere. When we look at the limb, we look not straight into the atmosphere, but we look at an angle. And now when we have a source function that decreases with height in the atmosphere, we see that when we observe the intensity for this center, when we look straight into the atmosphere, maps to a higher intensity than the source function, than the intensity at a ray that looks into the atmosphere at an angle, because that samples a higher layer where the source function is lower. And therefore, we get limb darkening. The intensity becomes lower because the temperature in the atmosphere decreases with height. Now, can this same kind of reasoning explain why we have absorption lines in the solar spectrum, at least in the visible? This is a section of the spectrum around 430 nanometers. This is called the G band because each of these little tick marks here indicates the position of a CH molecular lines, and there are so many of these lines that the intensity in this band is considerably reduced compared to wavelengths that are smaller or larger. So how come that we have these positions in wavelength where the intensity is substantially lower than the surrounding wavelengths, than at the surrounding wavelengths? Now, imagine that you have an absorption coefficient that varies very strongly with wavelength. I use frequency and wavelength interchangeably because you know that simply the speed of light is the product of the wavelength times the frequency. So whenever things vary with frequency, they also vary with wavelength. So let's assume that we have an absorption coefficient alpha that varies very strongly with wavelength. And now let's calculate the optical depth at the different wavelengths as a function of height. We know that the absorption coefficient is much larger at μ0, the center of the line, and we know therefore that the optical depth is a very much steeper function of height, or depth, if you will, the minus the height, than in the continuum at μ0, right? So now when you plot when you see where optical depth unity is on these optical depth curves, you see that optical depth unity in the line core is at a much higher height than optical depth 1 in the continuum. And now with the Eddington-Barbier relation, we know that we sample at μ0, the center of the line, we sample the source function at this height, and in the continuum, we sample the source function at this height, where the value of the source function is higher. So therefore, this strongly varying opacity through the line allows us to sample different values of the source function with height, and makes us that the emergent spectrum is has lower intensity in the line core because we sample a lower source function, because the opacity curve is much steeper, and therefore opacity 1 occurs much higher in the atmosphere than in the continuum. So this is a bit of a complicated diagram, but if you follow all the steps, you can see that this strong variation in opacity in combination with a source function that decreases with height gives us an absorption line. Because in the line core, we sample a lower temperature where the source function is lower than in the continuum, where we look deeper into the atmosphere and therefore see a higher temperature. Now, absorption lines dominate in the visible part of the spectrum. Once you go below 160 nanometers, you actually start to see emission lines. Now, how can we explain that? Well, in the same way, this first part of the diagram is the same. These two graphs are the same as in the previous one. But now we have a source function that actually increases with height. So when you sample this source function at the height where the line core optical depth is unity, we see a higher temperature and therefore get a higher intensity than when we sample the source function at the sample the optical depth unity of the continuum. We see a lower source function and therefore the continuum is lower. So again, the strong variation of opacity through the line with much higher opacity in the line core than in the continuum, in combination with an increasing source function with height, gives us an emission line. Now I showed you a little bit in the beginning, I showed you the calcium H and K lines. And the calcium H and K lines actually have, when you look very closely in the line center of this line, of these two lines, they have what are called small emission reversals. Now, can we understand that? Yes, actually in the same way we can understand that. We have a opacity that varies very strongly with height, with wavelength or frequency. And we have two opacity curves, one for the high opacity or optical depth curves, one for the high opacity of the line core and one of the wavelength here. Now, if we have a source function that first increases with height and then decreases with height, we can understand this because the line core intensity maps to this low source function value. The line, it's not marked here, but the intermediate opacity maps to the source function peak. And then there's a minimum here. And then the source function increases again when we go deeper. And so a strongly varying opacity in combination with a source function that first increases, then decreases, can give you a line profile that looks exactly like the H and K. Now, that doesn't explain why this source function behaved that, and that is much beyond the theory that we will present in this workshop. But this is how a line like this comes about. And I think that is my last section that I have for the line formation process. Now, these graphs, you have to really go through them and understand and try to think about them to understand them. But what I want you to take away again here is that the strongly varying opacity with wavelength through a spectral line allows you to sample different heights of the atmosphere. And when the source function is decreasing with height, you sample a layer that has lower temperature and therefore results in lower intensity. Now, name absorption line is somewhat misleading because this lower intensity in the core of the line is not due to more absorption at this wavelength, because actually even at this layer in the atmosphere, there's also more emission as a function of wavelength, except that as a function of depth, the intensity is much lower, or the temperature is much lower, and therefore the source function is lower, and the intensity that then appears at the surface is also lower. So the name absorption and emission line is a bit deceptive in the sense that it's not due to having more absorption. It is sampling different temperatures at different parts of the line. And in an absorption line, the higher layer is cooler than the deeper layer, where you see the continuum. So I will open it up for more questions if you have questions.
There are no questions in the chat at the moment, but if anybody has any questions, feel free to unmute and speak up or put your question in the chat window.
Yes?
So like, these plots are like always the hardest to go through. Like these are
Yes.
the most confusing plots to like understand, like for
Yes.
me. So what is the easiest way to get that? Because like in
Well,
simple terms,
the
yeah.
easiest way to understand is just look at this diagonal, right? In the line core, you have larger opacity, therefore you sample higher layers of the atmosphere where the temperature is lower, and this maps via the Eddington-Barbier in a lower intensity. And this is the most little bit of the confusing part of the graph. Because
Yeah.
you have to remember how opacity maps into optical depth. And this graph is included because you need to know where optical depth unity is.
Yeah, and so the top part, like the top of the absorption coefficient connecting to the tau, that is confusing because like that's not what you're seeing. You're seeing always the optical unit depth 1 for that line. That's the at the
well
at
this center, yes.
At this, yeah.
Yeah, but if you were to look at a different angle, these points would slide, right? You would have mu between 1 and 0.
Yeah.
And so you would sample this curve at slightly different positions, and slightly, for instance, if you would look at a mu that is slightly less than 1, you would sample even lower temperatures, so your line would actually become a little bit deeper.
Yeah.
Hi, Han, I have a question here.
Yes.
For sampling different height of the atmosphere, you can use different lines or use the same line but a different position, the core versus the wing.
Yes.
Just wondering, for one particular line, what's the height changes of the sampling from the core to the wing typically?
So in the photosphere for LTE lines, typically between the layer where the continuum forms and the line core forms is about 200, 300 kilometers, depends on how strong the line is.
Mm-hmm. Okay, the 200.
For chromospheric lines, it is up to a few thousand kilometers.
Okay, good to know. Thank you very much.
Mm-hmm.
There are no more questions in the chat at this time if you'd like to go forward.
So either no one understand anything or they understood everything.
Maybe many people have seen the slides before.
Well,
yes, we
many
have tried
people,
to.
I'm sure many people have seen this before, but really the important part is that different opacities at different wavelengths allow you to sample different height in the atmosphere. That is basically the main point that is. And so all the properties, in this case, we've only been talking about the intensity and intensity as a proxy of temperature, because we're considering LTE, where the intensity is directly related to the temperature. But all the properties at the given height that you sample are also translated into the different properties of the line, if the atmosphere moves at this height in the atmosphere, you will see that reflected in the Doppler shift of the line core. If there's a magnetic field, you'll see that reflected in the polarization at these wavelengths. So by measuring the polarization at different positions in the line, you also measure the magnetic field at different heights in the atmosphere. By measuring the line shift at different intensity levels in the atmosphere, you also measure the velocity shift or the velocities resulting in the Doppler shift at different heights in the atmosphere by sampling different wavelengths. So it's important to understand that really a spectral line is not only that it transforms the properties of the light in the sense that it introduces polarization, but the spectral line also allows you to sample different heights in the atmosphere.
So there is a question in the chat. Do absorption coefficient follow any general function given the same temperature profile?
Yes, so they are directly proportional to the density. And of course, the absorption profiles depend on the quantum mechanical properties of the line. So the stronger the line, the more probable the transition is to occur. The stronger, the higher the opacity, the absorption coefficient. So those are the main. Now, as a function of temperature, it could be that an atom starts to ionize when temperatures become higher. So then this absorption coefficient, the density factor there depends on the ionization level, right? So that gives also some different spectral lines, different sensitivities to temperature, because some of the spectral lines will disappear because the ion that they are part of will disappear with higher layers or higher temperatures.
The last question in the chat for now. Any more questions? I think we might be good for right now.
Okay, well, feel free to, if you have to take some time, go over the slides. If you have questions, post them in the chat and we can answer them when we come back.
Actually, Claire, should we create a channel for like lectures so that there are questions asked for the lectures rather than for the exercises?
Yeah, sure.
Sure.
Okay. So if there are no more questions, I think we can take an early break.
Yeah.
For lunch.
Sorry, I took less time than I thought.
That's okay. I mean, that's great. It seems, I mean, you were fairly paced. You were pacing well. So the Zoom will remain active in case the Slack is active. I've had a couple of questions about downloading the data and troubles with following that link. I don't know why there is some errors that sneaks into the link. I will post it again on the general Slack channel for people that have not yet downloaded the data. For this afternoon, I think we only need the Hinode, correct, Ivan?
Come again?
This afternoon, we only need the Hinode data. They don't need to download
we
all
only
of
need
it.
the Hinode data, exactly.
Okay.
Or for people who are super, who are super comfortable, they can use whatever they want. But yeah,
sure. But if they choose,
data.
one is 7 GB, might be slow,
Yeah.
Okay. So I will post the link there now in the general. Okay.
So what time do we reconvene then from lunch, from break?
We reconvene at 12:30 Mountain Time, which is 45 minutes from now.
45 minutes from now. So we'll leave the Zoom open. Feel free to either log out, or if you'd like to just leave yourself logged in, you may want to mute yourself and turn off your camera, and we will get started again in 45 minutes.
Claire, if you log out and log back in, is it free, or do you have to, there is a waiting room?
Nope, you can just log back in.
Okay,